This is the second of the two lectures on control volume analysis, and it has homework that goes with it. We will answer homework problems on Friday as well. So this isn't the last time we'll have a chance for you to ask questions, but I want to make sure we get through all of the material. I will say I was a little worried about getting through all the material, so I put up an online lecture that goes through all of these notes. And there are three example problems for the first part, the momentum equation part of this lecture. There are three example problems. I'm not going to have time to do all three problems in class, but you can see those on the online lecture. All right. And we have two new equations today. They're not completely new. They are, in cases where the flow is steady, and just to jump to the end to make sure we cover everything, we've got the two equations are momentum equation. And by the fact that we've got a steady flow and it's incompressible, so our continuity equation just becomes Q in equals Q out, which equals Q. You can, so these are the assumptions. This comes from steady, incompressible, and a non-deforming control volume. That's the first of the two equations. This is the only problem that I know of where you can, yeah, Cordell.
Is V2 a vector and V1 not a vector?
No, I just haven't gotten it up yet.
Gotcha.
Yeah, thanks. This is the only equation that of the ones that we most commonly use, that is a vector equation. It's also the one where when you're asked to calculate a force on a control volume, this is the only equation available to you for that. So that's the first of the two equations. The second one that later in the lecture is that again from doing a balance, not of momentum, but of energy on a control volume. This looks like the Bernoulli equation, It is the Bernoulli equation, but we're thinking of it now as as an energy balance. There are two additional terms. This shaft head term is included to consider the effect of having either pumps that add energy or turbines that extract energy. And I suppose we would say that, let's change that to plus or minus, because a pump would add energy to what's upstream, the turbine would take it away. And this new term, which we'll talk a lot more about when we talk about pressurized pipe flow, is referred to as a head loss. It's just a generic term for losses that occur in along the control volume from inlet to outlet. All right, that's the takeaway message, that there are these two equations that get used a lot along with continuity to solve these problems. In fact, I think every problem that you'd have in this next homework would be solvable with one or both of those equations together with continuity. Let's see some examples of situations where you use the momentum equation.
Let me get a paper towel.
Yeah, I'd say, because I don't know why our eraser is wet, but it certainly compromises there. Okay, so right, so this is not a lecture that's going straight from the start to the finish. I've started at the finish here. Now I'm going to show you cases where you can use the momentum equation, and then we'll solve a few of those problems. One would be we'll see if there's a water jet hitting a wall. The jet puts a force on the wall pushes back on that stream of water arriving at the wall. We're going to find that force F.
I can try it.
Oh, okay. Thanks. Time to do some erasing. Better. Thank you.
Mm-hmm.
So imagine we've got a pipe bolted to a nozzle and water, a particular flow with a constriction, higher velocity. We're given, say, V1 and D1, and then and the pressure V2, and asked to calculate the force necessary on the bolts that keep this thing together. That's solvable with the momentum equation. An open channel, a couple of open channel flow examples. This weir that constricts the flow will put a force onto the water. Flow under a gate. Water backs up behind the gate, comes out at a higher velocity. There will be, if you look at the control volume, this gate will put a force on the control volume. Flow around a bend, you'd have to put a force on that elbow to keep it stationary. We can figure out what that force is. Its X component, its Y component, given the pressures, diameters, and velocities upstream and downstream. All right, so just to say again, we have a steady state version of an equation that comes from the Reynolds transport theorem, but in our case it's steady and it's a non-deforming control volume. We have and just to emphasize, because it's commonly two common mistakes in these sort of problems by me and students as well, is one is that this force on the left hand side is the force on the control volume. And what that means is that in pipe flow, these external forces on the control volume includes the pressure in the pipe. And I'm going to do an example of that now to show you how all of this works out. Any questions? Questions out there so far? No, there's not much to. Okay, yes, I'm skipping example 1 that's in the online notes and going on to example 2 to find it's that problem. Flow around the bend. Let's maybe that was the dry one and this is the wet one.
This is pretty wet. I'm trying to.
Maybe you dry them out and then the water comes. Oops, this seems pretty wet, yeah. I thought I had a pretty dry one.
Want me to go upstairs and grab one?
You know, you could try going next door and seeing. I don't think there's a class in there, so I don't know why they were.
The camera's trained on those two cameras.
Okay. Let's decompose. Decompose that force that the control volume, that the bend puts on the water into a we do have to be careful about directions here, so I assume that f of x is in the negative x direction. Now you need the pressures on the inlet and outlet. This is a big water supply pipe. And so we think of there is this elbow, but what our control volume is actually the water inside that bend. So this is our control volume, and that elbow is actually putting a force on the water, and that's what we're analyzing. So we need the Q, so let's find one. All right. We need that Q. And now we need to specify the velocities, and we need their components. I will say that what I think is a good idea in these problems is to explicitly identify the external forces that are acting on the control volume. And so what I haven't done here is I haven't included the external forces from the pressure. So I'm going to say that there's a F1, that is the pressure in the pipe is pushing to the right because it's acting normal to the control volume here, and yeah, I'll get you just a second there, Cordell, and F2 is therefore the Y force that's acting in the negative Y direction that's equal to the pressure in the pipe acting on the control volume.
Is D diameter or radius?
It's diameter.
Okay. Pi r. Okay.
Right, pi d squared over 4.
Okay.
And usually when you get a statement like a 10-inch pipe, that means it's a 10-inch diameter pipe.
Okay.
All right, so we should then find the components of the velocity at the x location, or the 1 location and the 2 location. What I haven't said explicitly is that we want to find f sub x, f sub y. All right, so then what we're going to do is then say that and likewise where location 1 is inlet, location 2 is outlet. Now I'll ask you to supply those 4 velocities.
V1x equals 12.5 meters per second.
Okay, and it's positive because it's in the positive x direction, right? So 12.5. These are all in feet per second.
V2 of x is 0.
V2 of x is 0 because the water has turned and is going in the positive y direction. So that tells you that this should be
12.5.
12.5, and that's only because since the diameters have stayed the same, we have to have the velocities at the inlet and outlet location. You could get a problem where it gave you the upstream velocity and diameter and only gave you one of the downstream velocities or diameters and asked you to use continuity to find the other. In this case, it's all given to us. And this is 0. All right. And now let's calculate. There's a constant pressure and area. So we just need a single calculation for that. And I'm going to say F1. F1 is the pressure force at location 1. And it has its X component is the pressure at location 1. Let's see, it's converting to pounds per square foot times the area. I believe this is, somebody would confirm for me. Somebody with the Garrett there in the back, do you have a calculator?
$105.
5105? 5. Okay. Right, because the pipe's headed in the X direction, there's no F1 component in the Y direction. Likewise, okay, because the pressure, it's the pressure on the control volume of the pressure that's in the pipe, it's pushing in the negative Y direction, and that's why I have that as a negative. Okay, and I think what we want to do is use our equation. So on the left-hand side are the external forces, their X components, and that would be F1X minus F sub X. And then we plug in all the values and get what F sub X is. And, right, I assumed that F sub X, as a positive value, it would be pointed to the left.
What's the density?
Say that again.
What's the density?
Is that Cordell?
Right. What is the density?
What is, sorry.
Rho Q.
Oh, rho Q,
What is
right?
rho?
That's density,
Yeah.
right? Density times the flow we've calculated.
What is the thing we will call?
Oh.
For density.
What are the units?
The value.
The value. Oh, yeah, we do need to specify that. And it is in English units here, so that's a good question, because how do you figure that out? It's not something that it would necessarily know. You can remember this, gamma equals rho G, and so density is gamma over G. So that's in pounds per cubic foot, and feet per second squared. So you get that's the standard value for density in the English unit system. Okay, so let's put these values in. F1x, we said was 5105 minus f sub x, 1.938. What was it, 6.82? Yeah, 6.82. And v2x is 0 minus 12.5. And so move that to the right-hand side, and you get that multiply it out, we should get 5266. All right, so it's yeah, it's 5105 plus this 1.938. I get all of this as being 165. So can, go ahead, Garrett, just give me this times that times 12.5. Or Cordell, I see you with the calculator there as well. 1.9.
Oh, that's, yeah, negative 165.
Yeah, thanks. Negative 165, because that'll be negative 5105 when you move it over, and then you divide by minus 1, and you get that. So it is correct that the bend puts a force on the water in the left, to the left of a 5,266 pounds. Then it's all the same numbers, again, in the y direction, but useful to put all the terms in the equation. On the left-hand side are the external forces in the y direction on the control volume. You're going to get minus F2, and we said that it's in the positive y direction. And the way I think of it as, you think of where's the momentum at the start and where is it at the end. What you see here is there's X momentum that has gone away. And just like a jet hitting a wall, that occurs when you push on the control volume in the negative X direction. That's why I put this in this direction. You have no momentum, but then you do have you have no y momentum at the inlet, but you do at the outlet, X of y in the positive y direction. V2y was okay. questions on that? All right. Trying to think of the homework problems and think if there's a challenge. That I find one of the more challenging problems are the underflow gates. And so I'll just, in the way that I've done this, we have covered pretty much what I need to cover in the energy. Oh, there's a little bit more of that, but I'm gonna give you, at least set up a underflow gate problem. I believe there is one on the homework, and then we'll do a little bit more on the energy equation. Do you have any questions on this? Okay, good. So we have a gate and the water going under it. We're going to call this a 2D gate. That is, it's long in the direction. So we're given something we'll see in open channel flow. We're going to specify the flow per unit width, which is given a little q. So if we had a particular width of the gate, we would take the flow and divide by that width. If you think of it as a very long gate, you might just specify the flow per unit length, little q. So if we had a gate that was just 1 foot wide, what would be the force that the gate puts on the control volume? That would be one thing you'd find. And we specified only the flow per unit width. Oh, so we would, and we are given the upstream depth. So we'd have to calculate then these other things we're asked for. And what you know from continuity, if we're given the flow per unit width, So that gives us the upstream velocity. We can use the Bernoulli equation and continuity That's one equation that we have for the downstream depth and the downstream velocity. And then we also have this second equation trying to remember if there is one of these problems on the homework. I think there is. So it takes several steps. One, using continuity to find the upstream, the velocity, and then continuity and Bernoulli to find the downstream velocities and depths. And then once you've calculated that, then you can use the momentum equation to find the force on the gate. All right, and so if we look, let's just say we know all of those things. So once you know all of those velocities and the water depths, this is our control volume. Not fun sneezing with a mask on. But better than sneezing without a mask on, I guess. So, all right, so there's our control volume. And what's important to note is that the external forces on the control volume come from the pressure force that occurs in the water upstream and downstream. And you use an equation from statics to get fluid statics to get the hydrostatic force on the upstream side in the x direction and on the downstream side in the negative x direction to get those two external forces. So the external forces on the control volume will be three. There's the pressure force on the upstream side. There's the gate itself pushing to the left, and then there's the pressure on the downstream side also pushing to the left. And then that has to equal rho Q times the difference in velocities. And you're going from a V1 that's small to a V1 that's large. And that's how you solve those sorts of problems. And we don't have time to actually do one. There are solved problems of this sort that you can find on the Canvas page. And to finish up, I wanted to make sure we covered all of the parts of the Bernoulli equation or the energy equation that we need to. I've given it to you previously. Again, it's for steady flow. I said that this term, this shaft energy, can be added if it's a pump or subtracted if it's a turbine, but that on the right-hand side, there's always this head loss term. In our use of the Bernoulli equation so far, we've just oftentimes just neglected that. But in general, we're not going to neglect it. To do the problems now, we have to be told what the head losses are. There are also some problems where you can use upstream and downstream characteristics to calculate the head loss. There's one additional equation that you might need to use, is that you might be given the power that's added or subtracted from the pump or the turbine, and you have to relate that to the head added or subtracted. We're often given power added or subtracted. That can be related to the shaft head added or subtracted with this equation. This is, I see this referred to as the pump power equation. We're going to have a section on pumps, but one of the things that you'll discover is not all of the power of the pump actually gets added to the water. There's an efficiency factor, eta, that needs to be specified. And then what might also be specified, or what is specified, is the actual power added or subtracted. This is okay. And so you'll see this. Let me just finish up here and say that you might see it specified this way, where you're asked to calculate that power. And that's all we have time for. Okay? Problems worked in the online lecture, and we'll work more problems on Friday. All right, that's it.